So let me begin. So this talk is going to be about sim to real transfer of control policies for Lego robots. And I hope this is interesting. So we've been working on like sim to real transfer for Lego robots, and it's been working very reliable for us. So you can see this. We tested this outdoor using a robot donated by Naval Labs. Thank you for that. And you can see like this is purely a neural network driven. So there is single neural network that's controlling the robot and works pretty reliable. So I'm going to talk more about this later in the presentation. But first, I've been getting many questions about like the sim to real, and people are asking why it doesn't work for us. So I know like you could do this well, but we tried this in my lab and it didn't work for us. So today in this presentation, I'm trying to share the secret sauce of my research, which is going to be how we can transfer the policy. So if you don't know what sim to real is a method of training a control policy in simulation. And once you have this neural network parameters, you deploy the network on the real system. So here there are a bunch of obstacles you have to overcome, and I listed these 5. So in this presentation, I'm going to talk about accurate modeling, accurate simulation, accurate state estimation, adaptive control, dynamic randomization, and transparent hardware and software. Okay, so let's first talk about the first one. So I think you all know about this robot. This is Animal B version. So there's a newer version, Animal C, but this is the main platform that I use. So I've been working hard to train a control policy for this system. This was designed and developed by Robotic Systems Lab at ETH, where I did my PhD. If I give you a short list of spec, it's 32 kilogram. We call this a medium-sized dog, but it's a bit big-sized dog actually. The leg length is 60 centimeter. We have 12 actuators, and they are driven by the series elastic actuation. So if you don't know what that is, it's a mechanism that has a spring at the end. So instead of just a motor and gearbox, we have a additional compliant element at the end. So using this element, you can actually control the torque by compressing this element. So, Hooke's law, you know how much you have to compress the spring in order to produce the right amount of torque. And that's what we do here. Okay. And yeah, if I show you what happened if I try to implement this on the real system, this is how it works. So we train the control policy in simulation, we deploy it directly on the system, and it failed like this, right? So on the right is the same system. So we've been working hard to do system identification. So we for each link, we measure the weight. The inertia is hard to measure, but we estimate it as best as we can. The lengths are given by the CAD model, so they are pretty accurate. And so that's what we did, but it's still good, right? So we tried to figure out the difference. Of course, if it works well in simulation, and if it doesn't work well on the real robot, then that means there is a difference between the two systems. And we call this a reality gap, right? So what is the reality gap in this system? So the reality gap, so let's look at this system. So on the left, we have the control PC that's inside the robot, where we compute the where we evaluate the neural network, right? So we have the neural network parameters. Once we get the state, we evaluate the network and we get the actuator command. And that command is sent to the actuator over this delayed communication channel. And also this actuator has actuator dynamics, right? Because we have a spring, we have friction in the gearbox, we have lubrication, and many other things. introduce extra dynamics. And we didn't model this carefully. I mean, we tried to model this, but it's actually a very complex system. And it has to go through this actual dynamics. And then once the state changes, the state is sent back, or the measurement of the states is sent back to the control PC. Then with this information, it can compute the new actual command using the policy network. Okay, so we've been trying to model this with a traditional method. So this is a work by Dr. Christian Gehring. So he used a more traditional modeling approach to model the actual dynamics. So as you can see, we have different controllers in the system. We have motor electronics, motor mechanics, and spring mechanics, right? So we have these modules in cascade. So problem in this approach is that if there is a small error in the velocity controller, in the modeling of the velocity controller, maybe that's fine, like it's just a small error. But because there are many modules in cascade, these errors will stack up, right? Maybe these errors are effect is maybe multiplicative, maybe subtractive, we don't know. But in the end, what we found is that the end-to-end performance of the actual model was pretty bad. And also this takes a very long time to model, right? So you have to investigate each module, and you don't have all the parameters of the module, of each module, right? So you have to send some command, measure the input-output relationship, then you estimate the parameters of each module. So if you do that, this will take actually quite a long time. So I know like Christian Gehring or Dr. Christian Gehring spent about like half a year to model this properly. So we took another approach using a neural network. So here, instead of using an analytical model, because what we really care is the input-output relationship, or in other words, the end-to-end performance, right? So we model the whole system with a single neural network. And of course, on the right side, we still have this physics engine. Okay, this is a Newtonian mechanics, and it's got to be true, right? So we know that this Newtonian mechanics is correct, and we still keep it in the model. Right? So using this model, we could actually model the actuator much more accurately. So this red one is a learned model from the actuator network. This prediction is very close to the measured one, right? So yeah, this shows the performance of the learned actuator model. Then as we saw, we put this in a loop or simulation loop. So we combine this with a traditional physics engine and form a hybrid simulator. Okay, because this hybrid simulation, because there is a traditional approach of modeling of Newtonian mechanics, and there is an actuator part, which is modeled using a neural network. So using this system, we could actually achieve much better result in predicting the dynamics. So once we can predict the dynamics, we can use that simulation to train control policies for this robot, right? So in the end, we could train a locomotion policy where which made this robot run quite fast. We could recover from arbitrary configuration, and we could train a policy that can be robust against external disturbances, as you see on the right bottom corner. Okay. So the next is accurate simulation. So I'm not going to talk in detail because of time. What physics is inside this simulation in this simulator. This is RISIM. You can just get it from risim.com. This is the physics engine that I developed during my PhD, and I'm continuing developing this at KAIST. So you can see that, yeah, this is a general physics engine, but I've been mainly using this tool for reinforcement learning, and there are many utilities you can use for reinforcement learning. So, but you can simulate like a human model, can simulate different constraints. So what's nice about this simulator is that it's a hard contact simulation. Okay, so there, you probably know there is another popular physics engine. So this one is Mujoko. So Mujoko is soft contact simulation. So what it means is it actually allows a penetration of the field of contact points. So if you see, like on the left, the feet stays perfectly on the terrain. On the right, actually you see the feet penetrates the ground. Okay, so of course this is not realistic. You can actually tune the parameters of the simulation to make it look better. But then you have to tune this for every robot you try. And if you have multiple robots, you can imagine that this is actually a combinatorial problem, right? So that's not the proper solution. You might wonder, okay, if you actually want to simulate a contact, soft contact, then is it better to use soft contact simulation? But that's not actually true, because actually that depends on what simulator you use. But like this Mujoko, the problem is for every contact, even if you use the same parameters, every contact will show different behaviors. So that depends on the speed, that depends on the approaching angle. I mean, it's a complex system. And even if you see here, the feed actually penetrates differently depending on the penetrating condition. So of course, I don't know what's inside the simulation, but that's not a consistent behavior. Okay, so I argue that this hard context simulation is better. Nowadays, it's being used. So many people published using RISIMs, and I mean, it's good to see that it's not just my group, but everyone around also using RISIM and publishing good their research work using RISIM. So that brings me to the third one, accurate state estimation. So this one, because it's still under review, I'm not going to go detail in this topic, but I'm going to show you what we roughly what we did and how the robot performs. So this robot was donated by Sang-baek Kim's group, who's going to present at night or in Korean time. Yeah, and was manufactured by Naval Labs. I appreciate it. So this is a mini cheetah robot. It's about 10-kilogram robot. It's a much smaller robot, but we found that the reinforcement learning also works very well on this robot. So the idea is same. We train control policy in simulation. So here we also train a state estimation network. Okay, so that part is not published, so I'm not going to talk much about it. But if we learn the simulation or state estimation as well, it performs very well. So we tested on this very slippery terrain. And there are papers that show locomotion over slippery terrain, but I haven't seen like this fast locomotion on slippery terrain. Okay. So this is the baseline controller that we use to compare the performance. We tested like a bunch of different scenarios. So here we command like full speed locomotion, then we command this stop. Okay. You see how slippery the terrain is. We actually made it, we spread like some acid powder on top so that it's more slippery. So here you see, it's actually inevitable that you avoid slippage, right? I mean, you don't have perception system. Well, like we don't have perception system yet. That's why we cannot really avoid it. Well, it's just robust against the slippages. Yeah, we show like a locomotion over a slope, a slippery slope. And this is the part where you saw you can do locomotion outdoor reliably. Yeah, I'm going to skip this part because you saw this in the beginning. So then that's the next part, adaptive control and dynamic randomization. So I think these are like two factors that makes the policy more robust against unseen scenarios. In this part, I'm going to focus more on the adaptive control, less on the dynamic randomization. So for this work, we use another robot. So here you see like variety of very different robots of different sizes, different weights, and you can see that reinforcement learning actually works well on all these systems. So what we did here is we trained a so on MLP encoder, which maps privileged information. So these are information that you can obtain from simulation. So you can get a bunch of the properties of the terrain, so such as contact states, contact forces, terrain profile, friction coefficient, and so on. And you fed it to an MLP network, and you map it to a small latent vector. On the real, but because we don't have this information on the real system, on the real robot, you learn another network, a TCN encoder, which maps a history of information or history of observation to the same latent vector. Right. So once you train this, so this will try to capture information about this latent vector using the history of observation. Okay. This is something you can deploy on the real system. So if you do that, we can also deploy a control policy on the very wide environment. So I call this adaptive control because using the history information, you can estimate the unseen or like the environment properties, right? So what you're doing is actually adapting to the new environment properties. Okay, so this actually works very robust. I'm going to skip this quickly because I guess you saw the video before. So that now the last part, transparent hardware and software. So we've been working on this robot for 1 year. It's funded by Samsung. It's called Rival. So we completed this robot of like a few weeks before. It's a quadrupedal robot. And because I've been working on reinforcement learning controllers, I know how to design a robot for reinforcement learning control. And I know how to design a software for reinforcement learning control. And yeah, that's why I want to develop my own system. The robot is 26 kilo, 12 actuators. It actually has a lot of power. So it has over 10 kilowatts of power. That's like limited by the battery. It's not limited by the actuators. 60 Newton meter torque and 35 radian per second during velocities if the battery is fully charged. Okay. So there are different aspects of this robot. So I'm going to talk about electronics design, mechanical design, and software design. So for electronics, it's very important to design the whole system low latency. So for that, we use Elmo tweeter. So here we use EtherCAT controller. So we measure the latency of the system, and is below like 100 microseconds. So we found that that's sufficient for using an ideal model. So just ignore that delay, right? Because it's just cumbersome to model the aspects of the system. We wanted a system that's closer to an ideal system, right? And here the ideal system is like delay free, and 10 microseconds is close enough. Yeah, and we also the reliable power source is also important. For the mechanical design, this is also quite important. So here we don't use SEA. We use this quasi-direct drive or pseudo-direct drive, whatever you call, low gear ratio planetary gear system with robo driver actuators. So has low compliance, almost no compliance, and the friction is also very low. So we study different transmission systems. We design the planetary gears to minimize the friction. We also use this moment arm and design the system to minimize the friction. So that part is important. Software design is also important because it will introduce additional delay, right? So that was actually one big problem when we worked with animal robots, because their software has extra loops. There are multiple loops that you have to go through before you send your command to the actuator. So with this new software system, we want to avoid that. And we design the system such that we minimize the delay. Okay. And then we have this robot. So, so when we train the control policy for like mini cheetah, we still had to model the delay. We still had to model the friction in order to transfer the control policy to the real system. But here, it actually, there is no such modeling. So this is almost like ideal controller or ideal model. The only thing we did is modeling the rotor inertia. So that part is important. Other than that, it just worked out of the box. So we didn't have to model anything. We didn't have to train a neural network. Once we have a system that's reliable and that we can model, it just transfers very well. So yeah, here's my takeaways. So if you want to do sim to real well, then you have to think about these 5 factors: accurate modeling, accurate simulation, accurate state estimation, adaptive control, dynamic randomization, and a good hardware. Okay, thank you for listening and willing to answer your questions.
Thanks so much. Fascinating talk. And actually, we are using RaySim at Naval Labs Europe for our research with the mini cheetah. Certainly the fastest and the accurate simulator on the market today. So thanks again for your great work on that. So we have a bunch of questions. So Daniel, thanks for the nice talk. What are your thoughts on relaxing the accuracy of modeling simulation state estimation and do a final training phase in the real world instead? Do you think this is feasible or too data intensive?
That depends on what robot you have. So if you're talking about this quadruped robot, actually the amount of training data we need is, I think, is too much. Even if you do last training, you still want to run maybe 50 PPO iterations, and that's going to be too much on the real robot. So I mean, there are many other options. You can use multiple robots to collect data, or you can maybe use some of the real data and mix it with the simulated data. So there maybe there are a few other options, but we are not really working on that. We found it just much easier if you have a reliable simulation and you model your system accurately. Then yeah. So instead of using the real data, we chose to just make a reliable model for training, and that worked very well for us.
Thank you very much. A second question from Michelle. Is there a relationship between the actuator network and learning the state estimation? Does randomization relieve the need for accurate simulation?
Okay, so So when we did work on the state estimation, there was no actuarial network. So when we train a control policy for Minchita, we didn't use an actuarial network. So there is no relationship between the two. And does randomization relieve the need for actual simulation? Yeah, so that's the point. So randomization, dynamic randomization help you once if you don't have accurate simulation. So you just give a broad range and hope you shoot your real robot model. Of course, there are downsides. I mean, it will produce conservative policy, and which means it's not going to be highly performant, right? So that's the downside. I don't think this is going to work in all cases. So it's definitely something that you can try for your problem, but it's not guaranteed to work.
Thank you very much. Maybe a last question from Tommy. Great tool, thanks, first of all. Is designing the robot to match the simulator a big constraint for robot bodies?
Not really for us. So of course, there's some types of robots that you cannot. So just some types of robots that are hard to be modeled, right? So if there's like a complex kinematic loops, then maybe the friction properties are complicated and the computation takes too long. Maybe you need some simplification and so on. For us, what we had to do to design a robot for simulation is just make a simple robot, right? Don't add extra components. If you add extra components, they add extra dynamics, right? So just make the robot very simple. And again, like we use the idea from animal. We made the actuator modular. So all you have to do is model one actuator accurately. Then you can model the whole system, at least in terms of the actuation. Right? So for us, it's not really the constraint. It's actually a good robot design translates to a robot that you can simulate. But that's not always the case, of course.